Hey, so, astrophysics. Is that like you point a telescope at the sky and wait for pizza to fall? What's the actual point of it? How does it relate to, like, the regular physics you learn in school?
Peter, astrophysics is the branch of science that uses physics to understand the universe. Stars, galaxies, black holes, cosmic microwave background, and all that jazz. It's not about pizza, though that would be a delightful subfield. It builds on classical physics, Newtonian mechanics for orbits, fluid dynamics for gas clouds, and electromagnetism for how light behaves. But then it also needs nuclear physics and quantum mechanics to explain what happens inside stars and in extreme environments.
Honestly, it's amusing that you require a blow-by-blow explanation. Think of astrophysics as a hierarchy. Classical physics handles large-scale motion and gravity most of the time. Nuclear physics explains stellar fusion and elemental creation, why stars shine and why supernovae seed the cosmos, and quantum mechanics underpins particle behavior, atomic structure, and radiation processes. Isn't it enthralling how disparate domains weave together?
So inside stars, it's nuclear stuff, like they're giant fusion ovens. But then why do black holes need quantum mechanics? Aren't they just super heavy dust bunnies?
Good question. Black holes are governed by general relativity, a classical theory of gravity, but when you get to tiny scales near the event horizon or try to describe the birth of the universe, quantum effects matter. The big puzzle is merging general relativity with quantum theory into a consistent picture. That's where fields like quantum gravity aim, and why astrophysics often overlaps with fundamental physics research.
Which brings us to the math. One cannot flippantly discuss cosmic intricacies without differential equations, linear algebra, vector calculus, and tensor calculus for general relativity, complex analysis, probability and statistics for data interpretation, and group theory or advanced quantum math for particle behavior. Numerical methods and programming are indispensable for simulations. Fascinating, no?
Whoa, that's a lot. So is astrophysics more like being an astronomer with a math headache or a physicist with a telescope?
It's both. It asks, how do we connect observations to physical laws? How do tiny quantum rules create massive cosmic structures? What does dark matter and dark energy tell us about physics beyond the standard model? Those are open-ended questions that keep the field lively.
And perhaps the most delicious question, could understanding the cosmos reveal new mathematics or physics so elegant that even one as superior as myself will find it truly delightful? Victory ultimately belongs to curiosity.